Plate tectonics, the grand unifying theory of geology, explains all the geological processes occurring on our planet. It states that the surface of Earth is made up of thin solid plates, or crust, which float on the layer of molten liquid rocks beneath them called the mantle, and beneath that is the metallic core. Two main types of plates or crust exist: oceanic and continental. Oceanic crust, made primarily of basalt, is relatively dense and thin. It makes up the ocean floor. Continental crust, by comparison, is made mostly of granite, has a lower density, but is much thicker than oceanic crust. The discovery of plate tectonics began in earnest about 100 years ago when geologists working in the southern hemisphere noticed 1. The jigsaw puzzle-like fit between the Atlantic coastlines of Africa and South America, 2. Identical fossils, and therefore identical ancient organisms on the two continents, and 3. An ancient mountain range, split down the middle with half on Africa and half on South America. Alfred Wegener therefore proposed that the two continents had been joined together in the past and had since drifted apart, an idea he called continental drift. But his idea would not be accepted by geologists for another 50 years, when the mechanism for moving the continents was finally discovered. The plate tectonics discovery and continental drift videocast I have provided explain more about this discovery. We now know that Africa and South America were in fact joined together about 200 million years ago, and have since been moving apart as the Atlantic Ocean gets bigger and bigger through sea floor spreading. Deep in the Earth's core, large atoms such as uranium undergoing radioactive decay, where they fall apart to produce a smaller atom, release energy. It melts the rocks in the mantle above and causes them to move in convection currents, like boiling water in a pot on the stove moves. In some places, the liquid rocks in the mantle are moving upwards towards the surface of the Earth. This occurs at mid-ocean ridges and is where new oceanic crust is continuously being formed. The heat and pressure of the rising molten rock breaks through the solid crust above it. Molten rock seeps through the cracks, then cools and solidifies into brand new solid oceanic crust. To make room for this new oceanic crust, the slightly older crust on either side of the mid-ocean ridge must be pushed or spread away from the ridge in both directions. Once that new crust forms, it too will be spread away from the ridge to make room for even newer crust. And continental plates on either side of the ridge can also be pushed away from it as the ocean basin expands. This process is what separated Africa from South America about 200 million years ago, and is how the Atlantic Ocean grows larger and larger every year since. Some other prominent mid-ocean ridges occur in the Eastern Pacific, Indian, and also Southern Oceans. This map shows how the youngest oceanic crust is closest to the mid-ocean ridges where it forms, such as the Mid-Atlantic Ridge, and gets progressively older as you look away from the ridge. Older crust has been spread away from the ridge to make room for the newer crust to form. A brand new ocean basin and mid-ocean ridge are forming on Earth today in the East African Rift Valley. The Red Sea is actually the start of a new ocean basin that grows larger every year and is splitting the Arabian Peninsula and the extreme eastern coast of Africa away from the rest of the African continent. The clinching piece of scientific evidence that finally led all geologists to accept the ideas of continental drift and seafloor spreading comes from the record that Earth's magnetic field leaves in oceanic crust. Magnetic iron minerals in molten rocks will line themselves up with the Earth's magnetic field, which today points towards the North Pole. And this is the same way the magnetic iron needle in a compass works. When the rock cools and solidifies, the iron minerals are frozen in place and will always show what direction the Earth's magnetic field was pointing when they formed. But Earth's magnetic field reverses direction, or flip-flops, every couple 100,000 years in a poorly understood and unpredictable process. When reversed, the magnetic field points to the south, and any rocks that form when the field is reversed will have their magnetic iron minerals pointing south. If you examine the newest oceanic rocks closest to the mid-ocean ridge, their iron minerals point to the north, where the magnetic field points today. However, if you move away from the ridge in either direction into rocks older than 700,000 years old, all their iron minerals point south because at the time they formed, the Earth's magnetic field was reversed. If you move even further from the ridge into even older rocks, you encounter another zone where the rock's iron minerals point north. Still further away is another zone pointing south. The magnetic field has reversed direction many times throughout history, as the picture on the right shows. The pattern of magnetic reversals recorded in oceanic crust is parallel to and symmetric about the mid-ocean ridge. By the 1960s, geologists concluded the best way to explain this pattern is with seafloor spreading, validating Alfred Wegener's idea of continental drift from decades earlier. The production of new oceanic crust at mid-ocean ridges is balanced by the destruction of old oceanic crust at a subduction zone. In the picture above, the oceanic plate on the left-hand side is being pushed to the right towards the continental plate. Imagine a mid-ocean ridge off the left side of the picture. When they collide, the oceanic plate, because it is the denser of the two, will be forced to sink or subduct beneath the continental plate. This sends the oceanic plate down into the mantle, where it will melt and mix with the rest of the mantle's molten rocks. Because the oceanic crust started out as molten rocks from the mantle, you can say that subduction zones are going to recycle oceanic crust. Combining seafloor spreading and subduction zones gives us the basic model of how plate tectonics works. Upward moving molten rock from convection currents in the mantle breaks through to the planet's surface at mid-ocean ridges, where it hardens into new oceanic crust that is spread away from the mid-ocean ridge until it collides with a continent and subducts back into the mantle. Earth's surface today has 12 major plates. You should know about the Pacific Plate, oceanic, and the North American Plate, continental. The boundary between them is the San Andreas Fault. And everything to the west of the San Andreas is actually on the Pacific Plate, including Saddleback College. And the plates move at an average of about 10 centimeters a year, powered by the convection currents in the mantle. The picture above shows where Earth's continental plates were located about 230 million years ago. Back then, they were all clumped together in a supercontinent called Pangaea, and the Atlantic Ocean did not exist. Geologists are able to reconstruct this view by hitting rewind on seafloor spreading.